Hi everyone. Tonight we're going to go into the basics of titration, and it says part one because we're going to revisit titrations later because there's um, something called a buffer that we have to talk about, but we are not there yet. But we still need to know the basics of titration because titration is one of the most important experimental setups you need to know. It shows up on the test pretty regularly, so I wanted to split up the coverage into one that was just going into the background of what is titration, what is happening in titration, and then in a couple weeks we'll do a lecture that's going into the math of the various types of titrations. So, first of all, what is a titration? It's a procedure that's commonly used to determine the amount of acid or base in a solution. And a solution of known concentration that we call the titrant is delivered to a solution being analyzed. And this solution being analyzed is called the analyte. So please write that down. I forgot to include a space for that. In titrations, there is an equivalence point, which is the point in the titration where the moles of acid equals the moles of base. So whenever you have moles equaling moles, that should tell you I gotta use stoichiometry. So stoichiometry is going to be really important in titrations. The titration that you're going to do also involves an indicator dye, which is a weak acid or base that is added to signify the equivalence point with a color change. So this indicator dye, it's one color when it's in acid and it's another color when it's in the conjugate base form. And lastly, we have to talk about titration curves. And titration curves are a graph of pH versus milliliters of titrant added. So remember, titrant is the solution of known concentration. So let's get into some more details. So we should remember that the equivalence point is determined by stoichiometry only. Doesn't matter what the concentration is, doesn't matter if we're doing a weak acid or a strong acid, the equivalence point is always going to be where moles of acid equals moles of base. So we have to use stoichiometry to figure it out. The pH, on the other hand, of the equivalence point is determined by the acid-base properties of whatever conjugate is present at the equivalence point. At this point, all you need to know is that the pH at the equivalence point is going to be determined by whether the titrant is weak or strong. So if we are titrating with a strong base and a weak acid, then after the equivalence point, we're going to have a basic solution. And if we're titrating with a strong acid and a weak base, then after the equivalence point, we're going to have an acidic solution. So why is titration important? Well, there's two reasons to run a titration. The first is to determine the concentration of an unknown reactant. So please write that down. And the second is to determine the equilibrium constant for the reaction. And this note in the parentheses, we're going to revisit that when we start talking about the math that goes into buffers. So pH equals pKa at the half equivalence point. That's a unique situation that is going to be important when we start talking about buffers. This image on the right over here is an illustration of the titration. If they've got the analyte sitting in a beaker on a magnetic stirring plate, so here's the stirring rod. We are not going to be using a magnetic stirring plate. We are going to be using an Erlenmeyer flask, so that's kind of triangular shaped. And that's because you need to manually stir it, and if we use an Erlenmeyer flask, the solution won't spill as easily. The image also uses a pH meter. We don't have pH meters, so instead what we're going to do is use indicator dyes. And we'll get to watch a video soon about that experimental setup. So these boxes, there's two boxes on your note taker that have these labels. One is the burette containing NaOH of known concentration, and the beaker has HCl of an unknown concentration. So please copy those captions down. There are three major types of titrations. So one is a strong acid against a strong base. So copy down the example. Sodium hydroxide plus hydrochloric acid. Both of those are strong. At the equivalence point, this is going to be pH 7, neutral. The next is a strong base with a weak acid. So after the equivalence point, this is going to be pH will be greater than 7 after the equivalence point. And the last example is a strong acid with a weak base. And here the pH will be less than 7 after the equivalence point. So write down these 3 examples, maybe make a note of this pH. Okay, so here are 2 examples of graphs of the titration of a strong base with a strong acid. So in this graph, we're adding HCl, and in this graph, we're adding NaOH. So even though we are using different amounts of NaOH and HCl because our starting molarity was different, the equivalence point is the same. It's always going to be pH of 7. Okay, so we started with different molarities of NaOH and HCl. So here we started with an unknown concentration of HCl, and here we started with an unknown concentration of NaOH. The equivalence point is identical because that's the point where the moles of acid equals moles of base. And if it's the same, we just take the pH of water. Or if neither salt has is acidic or basic, we just take the pH of water, which is 7. So what's going on at the particulate level? There's some boxes on your note taker for you to sketch out some of these particles down here. So before we even begin the titration, before we start adding base, all we have is H plus and Cl minus. So take a note of the ion sizes here and that everything is fully dissociated because it's a strong acid. In this stretch of the graph, that's denoted by this bracket, we are slowly adding sodium hydroxide. And as soon as hydroxides, in this model, as soon as hydroxides react with H pluses to form water, they disappear from the particle view because they're just in the background. They've just become water. Okay, so as we start taking away those hydrogens, though, the pH starts to rise. So the more NaOH we add, the more hydroxide can neutralize these initial hydrogen ions, and the higher the pH becomes. Okay. At the equivalence point, all we have is sodium, and all we have is sodium, and what's going on in their picture? Okay, what should be in here is only sodium and only chloride ions. Yeah, I think they messed up the drawings here. What should be in here is only sodium and only chloride because at this point in the reaction, all of the hydroxides have reacted with all of the protons to give you a pH of 7. Because remember, the equivalence point is where the moles of hydroxide equals the moles of protons. And then up here, past the equivalence point, we're starting to have some hydroxide ions that can't pull out hydrogen ions to become water anymore. Yeah, so they did mislabel these. The white is H plus. Let me fix that here. This is H plus, and this is Cl minus, and that's true for all of these. So there was originally one hydroxide that came with this sodium, and it reacted with one of these H pluses to form water. So there's a H2O in the background in this panel. And then here we have only chlorines and sodiums. Okay, now the picture makes much more sense. Okay. So after the equivalence point, we start to have hydroxides that have nothing to react with, and so that's why the pH of the solution is basic. Notice how quickly the pH of the system increases at the equivalence point. It's perpendicular to the x-axis. The slope is 0. Well, is it 0? It's straight up and down. So um, at the this is a characteristics of what happens at the equivalence point, and that's one of the reasons why when we do a titration we have to be super careful, because this pH change happens so quickly. If we are like add an extra milliliter here, suddenly we go from a pH of 2 to a pH of 10, and that's how you know that you've overshot. Okay, so some features of the graph. So the graphs are on your note taker, so I'm not going to go back and look at the graphs when we talk about this, because you can look at the graphs on your note taker. So there's a neutral pH at the equivalence point. The solution contains only water at the equivalence, but that should be amended to say water plus salt, and salt in this case means it's the spectator ions essentially. So if we were to hypothetically need to drink the sodium hydroxide plus HCl, it should taste like salt water, but don't try that, because that's super dangerous and you don't actually know if you were doing it right or not. So, but in theory, at the equivalence point, it should taste like salt water. Don't try it. That's just the theory. Um, the shape is a S shape, and it's a sharp S-shaped titration curve. So it's very defined. The equivalence point is almost a straight line, and then afterwards it's also very it's not a very large slope. And there's no buffered region. So we're going to talk about buffers later. Just write it down for right now. Don't worry too much about it. So how did we create these titration curves? Well, one thing you can do is use a pH meter in software, which is the setup that was in that diagram that I had you guys label earlier. Or you can use stoichiometry to sketch out a titration curve, and this is much more likely. They love asking students to sketch out titration curves, so this math is actually pretty important. So let's go through an example problem. We have to determine the pH of a solution of 50 milliliters of 0.2 molar HNO3, a strong acid, as we add 0.1 molar sodium hydroxide. So this isn't saying, this isn't asking us to look at a specific volume of sodium hydroxide added. This is asking us to pick several time points, pick several volume points, and do the math to figure out what the pH is. Okay, we've picked out 4 points for you to look at. So the first is before the titration begins, no sodium hydroxide is added. What is the pH? Since HNO3 is a strong acid, all we have to do is take the molarity of the starting solution, 0.2, and take the negative log. So this is a very strong acid. The pH is less than 1. All right. The second volume point we've decided to look at is after we add 10 milliliters of 0.1 molar sodium hydroxide, what's the pH? So this is not an ice table because we're using moles here instead of molarity. We've set it up to look like an ice table, but it's actually just a way for us to keep track of the reactants and what is the limiting reactant. Okay, so where did these numbers come from? So before any reaction happens, we have to figure out how many moles of each we have, because that's how we do limiting reactant problems. We got to figure out how many moles there are of each reactant and which one is limiting. So to get this 0.01, we just did 0.2 moles per liter times 0.05 liters, right? This is 50 milliliters is 0.05, and that should give you this number. We did the same to figure out the moles of hydroxide, but with these two numbers. Okay, and pretty easily you should be able to see that the H plus is our excess reagent, and the OH is limiting at this point. So all of the OH is going to be consumed and become water, and what's left is this 0.009 molar, this 0.009 moles of protons. So the solution is going to be acidic because we don't have any more of this hydroxide and water is neutral. So we're going to take this, and remember this is in moles, and we want to convert it to molarity. So we got to figure out what the new volume is. And the new volume is we had 50 milliliters of the protons to start with, and we added 10. So we need 60 milliliters, or you can also express it like this, but it has to be in liters. And you plug the molarity into the pH equation, and you get a pH of 0.82, which is a little bit higher than 0.699. And that makes sense because there's a little bit less hydrogens, protons, I mean. The next data point, if you flip over your note taker, the next data point is what happens if we add 100 milliliters of 0.1 sodium hydroxide. So that means in our beaker now we've got protons, hydroxides, and water, and we have these two spectator ions, nitrate and sodium. So this is the amount of hydrogen that we started with. Okay, so this is still the 50 milliliters multiplied by 0.2 molar HNO3. And then this number here, remember all of these are in moles, so let me write that in. Moles. Okay, this number was obtained by multiplying these two together, except this would be in liters. So it's 0.1 liter times 0.1 moles per liter, and that gives us the moles of hydroxides. It's identical. The moles of each is identical. So since they're consumed in a 1-to-1 ratio, that means there's none of either left. And so our pH is just 0. It's just the pH of water. Okay. At the equivalence point, when we're titrating a strong acid with a strong base, the pH is just going to be 0. And last, so now we've overshot the equivalence point by 50 milliliters. So we're going to have excess hydroxide, but the question is by how much, so that we can figure out what is the pH here. So again, same math to do this, to figure out the moles. Remember, this is moles and this is moles. So we did 0.15 liters times 0.1 mole per liter to figure out the moles of equals moles of hydroxide. So that gives us this number. And then we did the same with the initial, which was 50 milliliters of HNO3 of a 0.2 molar solution of HNO3. Okay, so if we just compare, we can see that the H plus is totally consumed and there's excess hydroxide. So this is how many moles of hydroxide we have left, 0.005. So we want to turn this into a molarity by taking the new volume, so that's 150 milliliters plus 50 milliliters, or 0.2 liters. And then, but because this is the OH, we're finding the POH, okay? And then we have to do 14 minus 1.6 equals the pH, which is 12.4. So all of this was just stoichiometry. Even though we organized it in a table forms and it looked like an ice table, it was just pure stoichiometry. All right, so it's just a bunch of limiting reactant problems. The other type of titration curve is when we have a strong base and a weak acid, or a strong acid and a weak base. So both of these curves are in your note taker, but notice how the S is kind of weird looking now. It's not so defined. the the pH change at the equivalence point is not so drastic because now there's a little bit of slope to this area of the graph now. Okay, and the equivalence point is, in the case of the strong base, greater than 7, and in the case of the strong acid, less than 7. Let's look at what's happening at the particulate level. So you don't have to, I put in the boxes to sketch what's happening. Don't sketch out this whole molecule. Just draw like a big circle and just draw like a big circle and say this is like acetic acid. Ugh, the pen is skipping all over the place. I'm sorry. But there's no need to draw like all 10 of these little atoms. Okay. Before any titration happens, we just have particles of acetic acid in solution. And then as we add hydroxide, we start to get some molecules of acetic acid that have lost this proton. That have lost this proton. So they look like this instead. See, this one has no proton attached to it. And remember, in these drawings from this particular book, what happens is that as soon as the H2O is formed, it just fades into the background. They don't represent it anymore. So as we take away these hydrogen atoms by reacting them with hydroxide ions to form water, the pH starts to rise because the concentration of hydrogen is decreasing. At the equivalence point, we have only acetate ions. So this guy is called an acetate ion. We have only acetate ions and sodium ions. And then after the equivalence point, so this section of the curve looks very much like the curve of a strong base and a strong acid reacting together. That's because after the equivalence point, this curve is governed by the base. Okay, so that it has that in common with the strong acid, strong base one. Here, this is very much what a weak acid portion of a titration curve looks like. Okay, so after the equivalence point, we've got our acetate ions, we've got a bunch of sodium ions, but we also have hydroxide ions that don't have any hydrogens to react with. No H plus left. So these just stick around, and now the hydroxide ions are influencing the pH, and that's why the pH is greater than 7 at equivalence, greater than 7. Okay. We have to assume that the neutralization reaction goes to completion. That means that we assume that no acetic acid is being reformed. We assume that the reaction goes in towards this fourth panel and stays here. We assume that there's no backwards movement. So, some features of weak acid and strong base, or strong acid and weak base titrations. The pH will not be neutral at equivalence. The solution contains a conjugate at equivalent, and the conjugate has acid-base properties. And we're going to talk more about the acid-base properties of salts in the next lecture. It has a weak S-shape titration curve. So that's specifically referring to this area right here. And in these graphs, that's also referring to this area around the equivalence point. And then lastly, there are buffered regions. So buffers are made out of weak acids or weak bases and their conjugates, but we're going to go into that in much more detail next week or the week after. All right, we're going to be using indicator dyes, not a pH meter, because pH meters are expensive and hard to maintain. So indicator dyes, we have a lot of them, and we've used some of them before when we were investigating Le Chatelier's principle. So what are they? Indicator dyes mark the endpoint of a titration by changing color. The equivalence point is not necessarily the same as the endpoint, but we need to pick an indicator dye so that ideally they are as close together as possible. Here are some examples of indicator dyes. This is phenolphthalein. It's clear when it's in the acid form, and it's pink when it's in the base form. So this is often used in titrations, and this is the dye that we're going to use when we do our titration. So you're going to see your solution go from clear to pink, and this pink can get much more dark than this color. This is a picture of the pink right after it's completely changed. So this is the end point of the titration. If you overshoot this and um, add more base, then it becomes a much more dark and vivid pink. So come here, pen. Okay, so these H's disappear. Well, they don't disappear. They go away when when the molecule is transitioning to the base form. See, it's not here. And I know this kind of got cut off by the presentation, but it's this one actually says O negative. So those go away. Okay, here's another indicator dye. We've got methyl orange. So methyl orange over here is it goes from, oh, what happened? Okay, methyl orange goes from yellow to orange to red. So we've got a yellow form of methyl orange and a red form of methyl orange. So we've got a hydrogen ion attached right here, and then this nitrogen has a positive charge. The mechanics of why the positive charge happens specifically right here, not important. What is important is that you see that it gains a proton. So this is a base and this is an acid. So this is a base and this is an acid. And they're two different colors. And that's what's amazing about indicator dyes. The color change can tell us approximately where the equivalence point is. So indicators are weak acids that have a different color than their conjugate base. We kind of said that earlier. Each indicator has its own pH range over which it changes color. So we just looked at, this is methyl orange, but let's pretend we're looking at methyl red. And we also looked at phenolphthalein, which we know is clear down here, and then it turns pink up here. So they change colors at different ranges. So phenolphthalein changes colors up here starting around pH 8, and methyl red starts to change color around pH 4 or pH 6, depending on if you're trying to go from red to yellow or from yellow to red. So an indicator can be used to find the equivalence point in a titration as long as it changes color in the small volume change region where the pH rapidly changes. So in this case, since we're adding HCl, we would want to pick methyl red, because if we pick phenolphthalein, we're gonna end up stopping the reaction a little bit before the equivalence point. And if we pick methyl red, we're going to stop the reaction just after the equivalence point, and that's a little bit safer. If we were looking at a dye that changed colors like in this range, that would be a poor choice because it's too far. You might end up looking actually at this spot instead of at close to this spot. So ideally you want an indicator that changes color close to the equivalence point and maybe just after. Here's an example of a weak acid titrated with a strong base. So phenolphthalein changes color up here, and methyl red changes color down here. So based on this, we have phenolphthalein, which changes color right at the equivalence point. So that's the indicator dye that you want to pick. This methyl red is going to start changing color way before the equivalence point. So it starts changing to yellow. It's done changing to yellow before the equivalence point. So this indicator dye would give us no useful information about what the concentration of the acid was in the original sample of analyte. Whereas this, if we stop the titration correctly and we stop it right here at 50 milliliters, we're going to be able to figure out what was in our original analyte. Another example is this weak base titrated with a strong acid. So Here we've got our indicator, our phenolphthalein color change and our methyl red color change. And if we pick phenolphthalein here, it's going to start changing color around pH 9, and that's far before the equivalence point at like 5, pH 5 point something. So the phenolphthalein is not going to give us any useful information here. On the other hand, methyl red, which didn't give us any useful information in the last example, methyl red is going to be in the midst of a color change at the equivalence point. So it's going yellow to orange to red. So it's going to be orange over here and red down here. And so this is the dye that we want to choose because it'll help us stop at the right point. And this will not help us stop at the right point. And the right point is the point at which we can figure out how many milliliters of HCl did we add to neutralize this reaction, right? Because that's what the equivalence point is. Well, not neutralize, but where the moles of HCl equals the moles of whatever the base is. Here we've got a chart that shows you how many different types of common indicators there are. So there's an indicator for every equivalence point out there. And so if you're doing a titration and it's not, nobody's told you what indicator dye to use, you do some math and figure out where's that equivalence point, what pH is the equivalence point. And then if you say the pH is going to be 4 at the equivalence point, you're probably looking at using methyl orange or brome cresol green. Right, both of these, what just happened? Oh my god, sorry guys. Okay, if we say at the titration, at the equivalence point, the pH is going to be 4, then we're looking at using methyl orange or brome cresol green. If we say at the equivalence point the pH is going to be 6, then methyl red is useless to us because it's already yellow. Maybe this areochrome black or this alizarin, but not bromethymol blue because that's going to be yellow. But if pH is 7, then bromethymol blue will turn green right at pH 7. So if we're doing a titration where we know that the pH is going to be 7 at the equivalence point, maybe bromethymol blue is a good choice, or maybe phenol red. There's also a dye some of you guys may have used called universal indicator, and universal indicator is actually a mix of 4 or 5 of these indicator dyes so that it'll change to a different color at different pHs. And that, I think that's it. So on your note taker, I want you to sketch a titration curve for the titration of a weak acid with a strong base that shows why phenolphthalein is a better indicator than methyl red. So I'm going to go back to that slide so you can end the lecture on this and make sure that you get all the points that are in that little checklist. And we'll see you tomorrow. Bye.